Hello, my name is Max Schleich, and in this paper we present a technique to explain machine learning models that is based on notions from the causality literature. This is joint work with Leo Bertotti, Jordan Lee, Dan Suchu, and Fula Vagena. I would like to start with an example and consider Bob, who wants to start a business, so he goes to his bank and asks for a loan. Now in the background, the bank will run a classifier, and for Bob, this classifier returns no loan, so the loan is denied, and the bank replies, sorry, we can't do that. Obviously, Bob would like to have an explanation why the loan got denied. In order to generalize this approach, I will refer to Bob as an entity E star, who is characterized by a set of features. And on the other hand, we have a classifier C, which takes the entity as an input and returns the classification outcome. I will assume that the outcomes are binary and also that the classifier is a black box. So we don't really know what the classifier looks like. And in return, our technique is model agnostic, and we don't need to make any restrictions on the model that we are given. The goal is, of course, to provide an explanation for the outcome of the classifier. Now, in this paper, we present feature-based explanation scores, which are very simple. They assign a score to each feature, and the explanation is given by the feature with the highest score. So in this example, the explanation would be your loan was denied because of the number of inquiries to your credit history in the last 7 days, which is the feature with the highest score on the left. We consider two such explanation scores. The first one is the RESP, or responsibility score, which is presented in this paper. And it is based on the notion of counterfactual causes. The other score is the SHAP score, which is based on the notion of the Shapley value from cooperative game theory. And it has been previously used particularly in the medical domain. So in the following slides, I want to briefly introduce these two scores. I will start with the responsibility score and introduce counterfactual causes by an example. So let's consider Bob again and assume that he is characterized by 3 features: gender, age, and income. And as in the motivating example, the classifier C returns no loan for Bob. But there could be a hypothetical scenario where Bob has a higher income. So now he's able to afford a fancy hat and a nice suit, and suddenly the classifier returns loan. If this is the case, we would say that the pair of income and 1,000 is a counterfactual cause for Bob. We turn this notion of counterfactual causes into a feature-based explanation score. So the score for feature Fi is defined as the difference between the original outcome of the classifier and the expected value for the classifier where we fixed all features except Fi. So the score really gives us a measure of the influence of feature Fi on the original outcome. Now there's a problem with this score because a counterfactual cause does not always exist. And if that is the case, our score that we just defined will always be able to 0. So we would fail to give an explanation in this case. And the reason for that is because changing a single feature is not always enough to flip the outcome of the classifier. So in the causality literature, there are 2 complementary notions, namely the actual cause and responsibility, which extend the notion of counterfactual causes. And in a nutshell, they work by defining a contingency. So in our scenario, a contingency would be a set of features gamma with values W, such that if you change the original entity E star so that the features gamma take values W, you do not change the outcome by the classifier C by itself, but you are able to find a counterfactual cause for this updated outcome E star. So we can extend our feature-based explanation score with the notion of a contingency set. The goal now becomes to find the smallest set gamma, such that if we set gamma to values W in E star, the score will become non-zero. And if we are able to find such a contingency set, then we say that the responsibility score for feature Fi is proportional to the score computed for E star under this contingency. So this introduces the responsibility score, and I will next introduce the SHAP score. The intuition behind this SHAP score assumes that there is an order on the features, a total order on the features, and we want to compute the effect on the expected value of the classifier by presenting it with one feature at a time following this order pi. So let's consider an example. Let's assume that pi, the order, is given by F1, F2, all the way to Fn in that order. And then we can compute the contribution of F2 with respect to that order as follows. We would first compute the expected value of the classifier where we fix F1 and F2, so the first two features in the order, and also the expected value where we only fix the first feature. And the difference between these two expectations would be the contribution of F2 with respect to that order. And of course, we can generalize that. For a given order, we can compute the contribution for any feature by fixing the prefix in the order and then computing the difference between the expectations of including that feature and not including that feature. The Shapley score for feature Fi is defined as the average over the contribution of Fi for all possible permutations. So we don't just consider one order, but we consider all possible orders over the features, and we can compute the contribution for Fi for each order. So both the responsibility and the SHAP score require a computation of the expected value of the classifier, which in turn requires us to define an underlying probability distribution. Unfortunately, the real underlying distribution is unknown, but we have a sample T, which is typically the training data set in machine learning. We can make some simplifying assumptions to define this probability distribution over the sample T. One such assumption could be that the variables are independent, and then the probability distribution is given by the product of the marginals computed over sample T. We call this the product space in our paper, and we show that we are able to compute the RESP-score efficiently over the product space, but not the SHAP score because it would be sharp behind. Another assumption we could make is that the given sample defines our probability distribution. If this is the case, then we call it the empirical space, and in this case, we are able to compute the SHAP score, but not the responsibility score. So this shows that we need to compute these two scores over two different probability distributions. And in the paper, we present algorithms to compute these two scores using simple SQL queries. I want to quickly highlight a few of our experimental results. And here I focus on FICO data, where the task is to explain credit risk assessments. So this is very similar to the scenario I introduced at the very beginning. The classifier is specific for FICO data, and it is a white box model, which means that it is fully interpretable end to end. And because it is fully interpretable, we can define a white box explanation for this classifier, which is called the FICO score in our paper. This score is fully based on the given entity and the model parameters. Essentially, it tracks what the model does for the given entity. So the analysis we did is we compared our black box RESP and SHAP scores with the white box FICO explanation score. These three plots show the distribution of the top-ranked explanation per feature. So each bar represents one feature, And on the y-axis, we denote how often that particular feature was used as the explanation in our data set. And I want to highlight three key assumptions. First, the most frequent explanation is the same for RESP and FICO. So this is given by the first bar here, F0, and it is the most frequent explanation for both of them. However, when we consider F0 for the SHAP score, it is never a top explanation. And we believe that this is an artifact of the empirical distribution. And so we conclude that the FICO score, which remember tracks what the model does for a given entity, is more aligned with the responsibility score than the SHAP score. Or in turn, there are cases where the responsibility score can give a better explanation than the SHAP score. Another interesting observation is that the next two bars, feature F1 and F2, are very frequent for the responsibility score and also for the SHAP score, but not at all for the FICO explanation score. And the reason for that is that the effect of these two features on the outcome is only really apparent if when you change the values for these features, which is something the FICO score does not do because it is solely based on the given entity. It does not consider changing the features. And so we conclude that the counterfactual analysis that underlies the responsibility score can lead to interesting observations which we would otherwise not make for white box explanations such as the FICO score. And on that note, I end my talk and thank you very much for listening.